Each property in star CCM can be defined using various methods. A short list of these methods is given here. Constant, polynomial, thermodynamic polynomial data, transport constants, and table T. Let us see one by one the details of these methods. First is constant. Most properties have a constant method available which defines the constant value of the property. To change this property, select the constant subnode and make an entry in the value property. Then, next is polynomial in T. This is a method for calculating certain quantities as polynomial functions of temperature. The polynomial node represents polynomial coefficients for density, saturation pressure, and specific heat. Thermodynamic polynomial data. Thermodynamic polynomial data is a method for calculating specific heat with a piecewise fourth-order polynomial in temperature. Transport constants. Transport constants are a set of data that are imported from the transport properties file. Transport properties are used in kinetic theory for calculation of viscosity, conductivity, and molecular diffusivity. Table T. A material property that is imported from an XML file uses the table T property method. The data for the material property is contained in a property table that is represented by the table T material database table node. The property specific heat also has a thermodynamic polynomial data method available. How to set up our own material database? For this, we have to create a material folder. Right-click the material database node and select New Folder. We can also create our own material property. To create a database material property, right-click on the database material node and select New Database Properties. Select Database Properties with corresponding methods from the list in the Select Database Properties dialog that appears. The constant values for these new database properties are 0 by default. The Select All button lets you manage the selection of many items efficiently. Simply click it to select the entire group and then deactivate the individual checkboxes of the ones you wish to exclude. Click OK when finished. Let us see how the material data is used in the simulation file. It would be too costly in terms of disk space to duplicate all material data from the props.mdb file into every simulation file. Therefore, a simulation file only retains the information on materials that are referenced by material model selection. This information includes names of referenced materials, the database folder, that is, gas, liquid or solid to which each referenced material belongs, properties of referenced materials, values of the properties. To make data of other materials available, star CCM Plus accesses the props.mdb file directly. This action occurs when you want to replace a selected material. Available replacement materials are listed in the Replace Material dialog. Now, let us move our attention from material to solver setup or model setup. In this course, we are going to primarily focus on flow simulation setup and heat transfer simulation setup. Within flow simulation setup, we will study in detail how to set the laminar and turbulent flow problems along with boundary conditions and solver settings. Within heat transfer modeling, we will learn how to set up the conduction and convections problems. Star CCM Plus offers a wide choice of models for simulating flow and energy when the continuum mechanics formulation of fluid dynamics is valid. The coupled flow and coupled energy models are best for compressible flows, natural convection problems, and flows with large body forces or energy sources. The segregated flow model is used for incompressible or mildly compressible flows, particularly when computational resources are an issue. It is used with the segregated fluid energy models. Whichever flow and energy models we consider, we are going to use variety of models. Let us list them here before we go into details of model setup. First is the viscous regime models, which including inviscid, laminar and turbulent flow modeling. Then we have the equation of state, which are models that compute the density and the density derivatives with respect to temperature and pressure. Then we have the passive scalar models, which are transport equations for user-defined variables that can be represented using arbitrary scalar values. We also have the gravity model, specifically including the buoyancy source terms in the momentum equations. There are additional models meant for complex flow phenomena. Examples of these are thin film model, used for modeling de-icing or defogging on a surface such as a cabin windshield. There is also the porous media model, which is commonly used to show the macroscopic effect of the porous medium on the overall fluid flow. There is the non-reflecting boundaries and mixing plane interfaces concept, which allows accurate simulations of applications such as multi-stage turbo machinery. There is also the fans model, meant specifically for including the fan momentum source.